I have requested a new one. There's nothing I can do. I put new batteries in, but it is just dead. So I have requested a new one. Well, I mean, yeah, we have to have them for testing. So if I buy me a clock, I'm gonna buy a cool clock that is like got math stuff on it, and they won't let me use it for testing anyway. So they can buy me a clock. Yeah. So they should be able to get me a clock. All right. Okay. So, this section that we are starting today for Unit 2 is going to be our look at different types of functions and their relations to graph. So this is something that you start looking at as early as Math 1, looking at transformations of functions. In this class, we will focus we've already kind of focused some on logs and exponentials, looking at their graphs, but that's part of our focus. We'll also look at square root graphs and rational functions. Those are sort of like the advanced functions we're supposed to focus on more, but these rules all apply to all types of functions, so others will be peppered in that you have or should have seen before, okay? So what we're going to start off doing is just looking at the different types of parent functions, and then we'll talk about what happens so that we can transform those parent functions, because the nice thing is the rules are all the same for all the different types of functions. The way it looks when it's graphed might be different, but the rules are all the same. At the goal by the end of this unit should be that when you see an equation of a function, you should be able to have a rough picture of what that will look like in your head. So you should recognize what quadratics look like. You should recognize what exponentials look like. You should recognize what logs look like, square roots and whatnot. So you should be able to recognize those and be able to tell if there's a plus 7 here, that moved it up 7. If there's a negative here, that reflected it. So that you got a picture, maybe not a perfect graph, but a picture of what it should look like in your head. I cannot stress how important this is for your understanding of mathematics in the future. This is a really important unit for you to understand well, because if you are going beyond this math, it is something that you are going to be able to be expected to know well. So for your future in mathematics, it can be really important. So we want to make sure that we've got this. And you should have seen really pretty much all of this before. We're going to focus on some different functions that you may not have focused on quite as much before. So it should not be brand new to you either. So our first type of function that we're going to look at is just called the constant function. The parent function would be y equals 0. It is graphed there, but we can't see it. Because what is the equation y equals 0? Is it the x-axis or the y-axis? Okay? Alright. Caleb is correct there. Y equals is bad thing is once this happens, it's going to happen again today. So. All right. Maybe I can continue for now. We'll see. All right. So, this will be our x-axis here. Not our y-axis, but our x-axis. Is the y-axis a function? It is not. Because long ago, whenever you did functions, how did you test to see if something was a function? That vertical line test, right? So the y-axis is not a function because it does not pass that vertical line test. I feel it coming on. Okay. All right. Now, this is linear. That is a line. But it's a special type of line called the constant function. So when the line is horizontal, it's a special type of line called a constant function. We could refer to it also as the second type of function, which is linear. But not all linear functions are constant. Okay, constant is the special case of a horizontal. Okay, linear functions you should be very familiar with. Okay, the parent function for a linear function is y equals x. That is just a line that has a slope of 1 and a y-intercept of 0. I'm going to give you some linear functions along the way, but linear functions, while the rules of transformations do apply to linear functions, we generally do not use them because what did you learn in Math 1 about linear functions? There was a formula. It's like the one thing students usually remember. Y equals mx plus b. This works so much better than trying to do transformations with linears. So that y equals mx plus b is what we want to focus on when we're dealing with linears most of the time. Although the rules for transformations do also apply to them. All right. Our next type here, we've got this parabola. This is a quadratic. Just a little bit of language here. A quadratic refers to the function. The word parabola is talking about the graph. That's the shape that is made with the graph. So we would not call this a parabola function. We'd call it quadratic. You could call the graph, you could say the graph looks quadratic or that it looks like a parabola. Either one of those would be fine. Okay. Parent would be x squared for that. Okay. So these should all be ones that we're pretty familiar with. The next one, what's this squiggle right here? It's not exponential. Cubic. All right, so this is the parent graph for a cubic function. Now, cubics can do something like this in the middle, where they kind of go up and then back down. They can look like that. But the parent graph here, the x to the third, it just is like this squiggle that we have here. Okay. This next one that we're going to look at, this is one we will focus on. It's one that in our curriculum says that we need to focus on. And this one is a square root. You may sometimes see this called radical, but radical could refer to any type of root. It could be a cube root, fourth root, fifth root, whatever. Specifically, we will be looking at the square root function, so we'll use that more often. With the square root function, this graph ends right here. It has an end point, and then if you wanted, you could put an arrow on this end. And that would be a closed circle. That end point is included there. Okay. What's the V shape? That's absolute value. We'll use this one some, but this is one that's really focused on in Math 3, so it won't be our main focus, but you'll see them some. I promise that you did. Alright, so this next type, this is another one that we're going to focus on in this class, although it is also one that is in Math 3 quite a bit too, but this one's definitely one where that overlap happens. Whenever we have 1 over x, that is rational. And it will be one that we focus on in this class. And then there are a couple others we've already looked a lot at, but we haven't really done transformations with them so much. We've seen ones with transformations, but we haven't talked about what those transformations were yet. And that would be logarithmic. And I put the parent function as natural log of x, but really it's whatever log is your base. So it could be natural log of x, or it could be like log base 3 of x, or it could be log of x. It could be, any type of log there. And then our last one here is exponential. And we should be able to recognize those as well. Logs and exponentials we will continue to focus on. We had the whole unit, the last unit was on logs and exponentials, but we'll continue to look at those pretty in depth as well. Logs and exponentials we'll look at quite a bit, although we focused on them some in the last unit, so it'll come from there. Rational and square root are going to be the big ones that we look at, although any of these may show up, but we will have separate sections looking at the rational and the square root here. So let's talk about transformations in general, okay? The cool thing is that these work for all functions, right? So it's going to work for any of those functions that I just listed. It could work for other functions outside of that, things like something to the 4th power or a cube root or something like that. But we're going to mainly focus on these functions that have been listed here. What we see is if I put a negative in front of the function, okay? Notice what's going to be next, negative on the inside of the parentheses. So this is a negative out front in front of the whole thing versus the next one we'll look at will have a negative inside of the parentheses. If we think of, I like using squares as the easiest example. So for example here, if we're thinking of this, it could be like y equals negative x squared. Okay, this makes the entire function negative. The change to the parent graph, what's this one going to be? Who remembers? Reflection over what? over x-axis. Okay, flips it upside down. So it takes whatever the parent function looks like and it flips it over that x-axis. Okay? Now the difference here would be, like if we're thinking about an x squared function, for the next one, it would look like this if I had a negative on the inside of the parentheses. So the negative is on the inside of the parentheses here. What does that do differently? Here, let's graph these two on Desmos and see. So you don't need to get out your computers. I'll just graph it up here for us. So there's the parent function. So I'm going to do, so you can see this one we just did, right? If I put the negative out here, it just flips it over that x-axis. All right, what about if I put the negative in the parentheses? Ooh. Does it never do anything? Okay, let's try this. X to the third. Negative x to the third. It changed that one. Alright, it's reflecting over the y-axis. So, if I change these back to squares, what is this one going to look like if we flip it over the x-axis, or the y-axis? It looks exactly the same because the y-axis is symmetric. It's symmetric about the y-axis. So, for some functions, this looks like it does nothing, right? If I change this to absolute value of x, right? Absolute value of negative x looks exactly the same because the y-axis is going to be an axis of symmetry there. It does nothing to the graph. Although it would help if I did that right, but it still does nothing to the graph, right? It's just reflecting over that y-axis. It looks the same. So for some of these, it's going to look exactly the same. But it's reflecting over the y-axis. For some, it's going to make a big difference, like square root of x, oops, and square root of negative x. See, that makes a big difference in our graph. But for others where it is already symmetric about the y-axis, it doesn't make a big difference. Flipping it upside down almost always makes a difference as long as you're starting with a function. But sometimes for these, it actually doesn't look any different. So this is a reflection over the y-axis. Alright, the next one, f of x plus c. This time we're adding c to the end of the function. This would be something like this. If we're just sticking with those square examples, y equals x squared plus 3. What is that going to do to the graph? Okay, it will change your y-intercept. Speaking of like the whole graph as a whole, it moves it up or down. So it translates up or down c units. So if we put a plus 3, it is going to move the graph up 3. If we put a minus 7, it would move the graph down 7. And it does affect that y-intercept, but it's not just the y-intercept, it's the whole graph goes with it. Alright, inside of the parentheses, that would be something like this. X plus 3 is added together and then squared. Alright, what does that do when it's inside of the parentheses? left or right. And like this +3 right here, which direction would it go? It would go left. It's the opposite direction of the sign that you see there. Okay? So it's going to translate left or right, C units in opposite direction. Meaning that if you have a positive, which normally on the x-axis, positives are over on the right, it is actually going to make you go to the left. If you have a negative, you're subtracting 3, normally negative is on the left, it makes you go to the right. Okay, questions? Okay, let's graph these real quick just to see what's happening. I got f of x equals x squared. You can see if I add 3 to the end, it's going to move it up. If I made it like -6, moves it down 6. That number on the end moves us up or down. But if I put parentheses here and put a +3 right here, we can see that even though I added 3, that would make me think I'd end up over here at +3. It actually went the opposite direction and went to -3. Here. The reason that happens here is because you're adding to your, let me think of how to explain that. Basically, anything inside of the parentheses ends up being opposite of what you think it should do. It is in general, if we think of like graphing, if we think of x squared, right? 0 squared is 0, 1 squared is 1, 2 squared is 4, 3 squared is 9. You got those points. I'm going to put -1 is 1, -2 is 4, -3 is 9. So that just puts our points on our graph right here. What is happening here is it's basically like we're adding 3 to our x coordinate, but not to our y coordinate. So that doesn't want to do that. So like, oh, I got rid of that altogether. So that would be like 4. That would become 5. That would become 6. Hold on. No, I'm telling you the opposite explanation. Let me think on the explanation of that. I will have a better one. You asked me. I need to think about it a little bit more before I explain that. I promise it is true, though. It'll be the case. So take my word for it for now, but I'll get you a better explanation for why that is. Because I know I've got one, but it's just not coming to me right now. All right. Okay, I'm going to write down over here on my long list of things I got to do. Okay. All right. Now we're getting to, so this covers our reflections and our translations, up, down, left, right. I generally find those the easier ones to deal with. The stuff that's coming up, I find it more difficult. Okay. what's coming up is our stretches and our shrinks and horizontal. I'm telling you, it's important. You got to know it. So if you didn't like it last time, guess what? It's back. Look, we're not talking about what did or did not happen in Math 3. We're fixing it now. If you don't know it, we're going to learn it now. We're not going to complain about it and say we can never learn it again because we didn't learn it the first time. Yeah, he can. Yeah, that's pretty impressive that he can bend the bar. But we must learn how to do this now because it's back because it's important. Is the reason that it is back. Because it is important for knowing this. So, whenever we have a number, why is it not let me draw right now? What's happened to it? Did I click? Okay, there we go. All right, so if we have a number that's multiplied on the outside of the function, that would look like this: y equals 3x squared. And that number is greater than 1. Okay? Then that is going to be what we call a vertical stretch. Or really a better word than stretch that you're going to see. I'm going to do it this way. I'm going to say the better word is expansion. But sometimes some textbooks do use the word stretch. Here, so what that's going to do is it takes your graph. It's like you grab it on the y-axis and you stretch it and make it taller. Okay? This is what happens if that number is greater than 1. Now, what about if that number is smaller than 1? And we're not going to include negatives because negatives are reflections. So we're not going to think about negatives. If you multiply by -2, you think about the negative and the 2 separately. The negative is a reflection. The 2 is the number that you look at. So what about if I multiply something by a number between 0 and 1? Okay? That is a vertical. The word that I see most often is compression, but some textbooks do use the word shrink. So we want to know both of those in case either one of them get thrown out there. Because if we multiply a number by 1/2, it makes that number smaller, right? So this is like taking the y-axis and squishing it, right? Now, if we take something and squish it, what can be a little confusing sometimes is it makes it look shorter, but what also happens, like if you took me and you squished me down so I was only like 4'5", but my weight didn't change, what would happen? I would look a lot wider, right, if I was super short. So the same thing happens to the graph. When you squish it down, it's also going to make it look wider. It's shorter, but it's also wider. Same thing when you stretch it out, it's going to make it look taller, but also thinner, right? Because if you are, 6'7", you're pretty tall. But if you are 6'7" and weigh 350 pounds, you don't look the same as 6'7" and 200 pounds. Somehow you look taller to me if you're skinny and but it'll make it skinnier and taller. So sometimes it is difficult to tell by looking at the graph exactly what's happened here, or thinking about what these look like. We'll look at some ways that we can tell what is going on there. And notice that both of these were vertical, and the C was on the outside. So I didn't write an example for this, but this would be like y equals 1/2 x squared. So that C is multiplied on the outside of the parentheses. Now, on the inside of the parentheses, okay, This is also going to cause expansions and compressions, but on the inside of the parentheses. So when that C right there shows up on the inside of the parentheses, we are going to have a horizontal, okay, compression. Now, this seems backwards, because right here, this is where it says C is greater than 1. The example here would be something like y equals 2x squared. Right? I put a big number in there. If I say big number when we're talking about this, I mean a number that is greater than 1. Right? So I put a big number there, but it caused a compression. Right? So anything inside of those parentheses, the opposite happens. When you put a plus 3, it actually moves it left 3, right? Same thing with expansions and compressions. If you put a big number in, it actually makes it smaller. It's a compression. So it's backwards from what you see. Whereas vertical is just straight what you expect. If you put a plus 3 on the outside, it moves it up 3. If you multiply by 3, a big number, it makes it bigger. It stretches, okay? So this is horizontal compression. You need to think x-axis here. So that means you're taking your x-axis and you're squishing it, right? Now, if we think about what that's going to do to a graph, if we take our x-axis and we squish it, or if we take anybody and we squish it, right, it makes it look taller, right? So sometimes horizontal compressions can look like vertical expansions. And so the way that you can tell is by looking which one is happening there, is by looking at the equation and being able to tell that. If we have a number between 1 and 0 here, so something like this, y equals 1/2 x squared, like so, we're putting a small number there. When I say small, I mean between 0 and 1, right? If we put a small number there, it actually causes a horizontal expansion or stretch. Okay. Now notice here, this is important to notice, horizontal is whenever we have that C on the inside of the parentheses. And expansions and compressions all happen with multiplication. Adding and subtracting, that's our translations. That's up, down, left, right. Okay? So all 4 of these are multiplying. That's where we're going to see them. All right, and let's just do an example. I'm just going to graph an example to show you what in the world we're talking about for the last one. So the last one is to take the absolute value of the function. This is different than having an absolute value function as your parent graph. So sometimes absolute value is your parent graph. You're just starting with that V shape. All right. So if we look over here, and let's say that we've got the function, let's just go ahead and do something like 3x to the second minus 4. We could even do something like this. Let's make it more complicated. Okay? So if I have a graph like this, right? If I do the absolute value of that whole function, 3x plus 7 squared minus 4. Okay, so my absolute value bars are on the outside, and I've got all that stuff in the middle. 3 times x plus 7 squared minus 4. The quadratic is my parent function. What did it do to the graph? The purple graph was this one. Oh, wait. Right? I had this parabola. Then I've got this one. And Caleb, what did you say? It reflects the negative portion of the graph. The positive portion of the graph stayed exactly where it was, right? But the negative part is flipped over the x-axis. It's almost like it turns that negative part inside out. It's sort of like what's happening. This is like sort of like a sock that's halfway inside out here. And this could be the case with like any function that you start with. If I started with square root of x plus 2 minus 6, something like that. Actually, let's make that minus 3 just so it'll fit on our graph a little bit better. If I do absolute value of that stuff, see how it looks here? You know, here was our purple function. And then whenever we reflected over that x-axis, it took all these negative parts and flipped them upside down over the x-axis. So those are kind of weird. So it reflects negative portions of the graph. Over the x-axis. That's one you may not have looked at in Math 3. Okay, questions there? All right, so let's talk a little bit more about those expansions and compressions, because I want to talk about exactly by how much this is happening, okay? So, when a number is inside of the parentheses, the graph will behave in an opposite manner than you think it should. For example, a positive number added to the x will make the graph move in the negative the negative or the left direction. Okay. A larger coefficient, when I say larger, here I mean greater than 1, in front of the x, will result in a horizontal compression, while a smaller coefficient will result in a horizontal expansion. So, yes, it doesn't do anything if it's equal to 1, because multiplying by something 1 doesn't change anything about it. So if it equals 1, it'll just stay the parent function for multiplying there. I've got a couple here, and I did this in Word specifically because I wanted to be able to show you what happens. So, like, if you have a vertical expansion, it is like you take this picture here and you grab the y-axis and you stretch it out. So you can see what happens if I do that, right? It makes the graph look taller and also skinnier, right? We're not changing how wide it is, really, we're stretching it vertically. Whereas if I have a vertical compression over here, it's like I took the y-axis and I squish it, right? So it would look like this, right? Really, left to right, nothing's changing. It didn't get any wider there, but it looks wider now, right? Because it's shorter, which makes it look fatter. All right. Horizontal expansion and compression is the same idea, but this time you're grabbing the x-axis and squishing it or stretching it. So horizontal expansion is going to look like this. Oops, not go quite so far because it disappeared. So it stretches it this way, making it look wider, which in turn also kind of makes it look fatter, right? And then if you have a horizontal compression, if you change just that x-axis, it makes it look taller, but really what you're doing is you're squishing it this way. So hopefully that helps you sort of visualize what's happening there. So whenever we talk about expansions and compressions, we talk about the factor of expansion or compression. For vertical, remember vertical is when we have that number multiplied on the outside of the parentheses. Okay, for vertical expansions or compressions, we would say that they're expanded or compressed vertically by a factor of a, whatever number it is. So if it's y equals 3 times x squared, we'd say it's expanded vertically by a factor of 3. We just use the number as it is. Things on the outside of the parentheses work as we think they should. Things on the inside of the parentheses are backwards, right? So whenever we have one of these horizontal expansion or compression, our A is going to be on the inside of the parentheses. And we say that it is expanded or compressed horizontally by a factor of 1 over A. So for example here, if I've got y equals 3x squared, I'm multiplying by 3 on the inside. The inside of the parentheses tells me this is horizontal. 3 is a big number, so what's it going to do? Shrink. It's going to be a horizontal compression by a factor of 1/3, not the 3. For expansions or compressions, if you are expanding vertically or horizontally, if you're expanding, you should have a number that's bigger than 1. If you are compressing, you should have a number that's between 0 and 1. So that means here, because everything's backwards, we've got to do 1 over that number for that to happen, right? All right, so let's look at picturing what's happening with this graph. These graphs. So we're going to tell the parent function and how it relates to the graph. So we need to know the parent function and the transformations that have happened. All right. So let's see, Reagan, what parent function are we dealing with number 1? That's quadratic, yes. All right, and we can tell this is quadratic because of that square right there. That's what tells us this is quadratic. So that 2 is not a transformation. It's part of the parent function, right? But it does mean that we've got 2 transformations here because I got that plus 3 that's not usually there in the parent function. And I also have the minus 2 over here. So, please feel free to refer back to your table if you need to there. Miles, what does the minus 2 do on this graph?
It sends you the right 2 units.
Nope. Outside of the parentheses is going to be up or down. So, here, add it on the end here. This is going to be down 2. So, that minus 2 tells us that we go down 2. All right, Valeria, what about the plus 3? What's that going to do? It goes left 3. So that plus 3 tells us that we go left 3. So those numbers added or subtracted on the inside, they tell us to go left or right. They go opposite direction. We had a plus 3 here. So instead of going the positive direction, we had to go negative, which for left or right is your left direction. Okay? All right, let's see. Lily, what's our parent function for number 2? Okay? Is it a square root? It's not. We don't see a square root anywhere. Is it a quadratic? No, we don't have a square anywhere. What do we see? We got this little third power here, right? Actually, let me try to stick to my color coding scheme here. I'm just highlighting randomly. So that 3 right there, that's what tells us what type of function we're dealing with. It's a cube, so this is a cubic function. Okay, so the parent function would just be x to the third. I have got this 3 right here on the inside, and it's multiplied by my x. So what do you think, Luke? All right, is it a horizontal or a vertical shrink? It's on the inside of the parentheses, so that tells me horizontal. It is a big number. When I say big, I mean anything bigger than 1. So big numbers actually do the opposite. They shrink here or compress. By, what's the factor, Luke? 1/3. Because we got to do 1 over the value for that. All right, Mallory, what's our parent for number 3? Square root, very good. All right, and it's a little hard to highlight there, but that square root obviously is what tells us it's a square root. Now, square roots don't have parentheses, but pretend there are parentheses around whatever is inside of the square root. Okay, so that means we actually have 3 transformations here. Okay, so let's start with this plus 3 right here. So, Bo, what will that plus 3 do to the graph? Very good. Left 3. All right. Then, let's think about that 5. Owen, what will the 5 do? That's perfect. It's a little bit confusing because it's sort of like in the wrong place. But it would be okay to write this way, negative square root of x plus 3, and put that plus 5 over there on the end. That would be equivalent, and that would look a little more like we're used to seeing. So it is going to be up 5 because we have that. Now, What's the last transformation? What? Okay, I've got this negative right here that I could think of it's like a negative being multiplied by that square root. So that negative, is it only inside the parentheses or the outside? Outside, because our parentheses are basically like our square root in this case. So that is going to reflect over our x-axis. Yes. All right, so make sure we get time to do this one. Let's skip down to 5, because 5 can be confusing. What is the parent function for 5? Anyone is rational. And we know, I can't really highlight this necessarily. We know it is rational because it's got an x in the denominator. All right, if you have an x in the denominator, that's going to make this rational. Now, the parent for rational is like this, 1 over x. So this does not have parentheses, but I could put parentheses right here. Also, that 3 just kind of turns to, that 1 just kind of turns to a 3 in the top. So when I see this, I can also think of it like this. I can write it like this, 3 times 1 over x plus 2. Because if I multiplied that back together, that'd be 3 over 1. I'd multiply the numerators together, which would give me 3. Denominators together, x plus 2. So that 3 you can sort of think of as being like on the outside there. And then, you've got this parentheses around that denominator there. So it is multiplied and it is on the outside of the parentheses. So if we look at this plus 2 right here, let's see, Lucian, what will that plus 2 do for us? It is going to go left 2 there because that denominator is like it's got parentheses around it. Very good. Then we have got to consider our 3, which we can think of right here. It's that 3 in the top also. So, Joshua, what do you think for that 3? Vertical. I'm going to use the word expansion by a factor of 3. But stretch is fine. Stretch is is a word that you see sometimes. Yeah. Vertical is because it's on the outside of the parentheses. So that's kind of why I wrote it this way over here, because rationals look a little bit funny. So vertical is because it's on the outside. And when we're talking about vertical expansions, big numbers do what you think they would do. They're going to expand. They'll make it bigger. Okay? All right, we didn't quite get through all of these, but it's more of the same rules. Let me show you your assignment for tonight. It is going to be on Desmos Classroom, which I don't think we've used yet in here, have we? No. All right, so it should on Canvas, if you click here, it's going to have a link that hopefully works to add you to the class. Okay? Then once you do that, there's going to be something called the functions card sort. And it is going to have you go through and like sort cards to match graphs. Okay? So use what we have learned here by this. Do not graph them in Desmos except for as a last resort. Okay? Because I know everybody can type those into Desmos and see what they look like. I want us to be doing this without a graph. There will be a non-calculator section to this test. So only do that as a last resort.
I saw that there was a command for the test review.
It is optional. No, you do not have to do that. It was just some people had asked for some extra questions. So only if you want extra problems.
What's the difference between vertical compression and horizontal expansion? Or is there none?
They can be the same sometimes. Like, for example, if you're doing like y equals 2x squared, like if you distributed that sort of, squared both of those, you get 4x squared. So a horizontal compression by a factor of 1/2 is the same as a vertical expansion by a factor of 4. So that's why, like, answering these questions, it's important to know like what you're looking at for the functions. Now, if it was like a graph problem, you could talk about either one, which there wouldn't be. Both of those would not be given as answer choices, right? I won't give you both of those answer choices because most of this is going to end up being multiple choice when you see it. So I would not give you both answer choices because they could both be correct. If it is written this way, probably what I'm looking for is horizontal compression by a factor of 1/2. But if it is like maybe you got to match it to a graph, you could think of it either way for that. Good question.